Hi guys, in this little video what I'm going to do is do some of the problems from the homework. In particular, I'll do all the ones that people had asked me about from the homework. Most of them are from chapter 3, and also I'll go over solutions from quiz 2. Okay? All right, so let's start with this. Quiz 2 says if 2 of your 4 friends have taken a particular advanced math class and could help you with understanding a problem, you absolutely cannot remember who took the class, so start calling your friends to find out if they can help you. Find the probability that you finally get help on the 8th try. Okay, so what do you have? You have 2 out of 14 friends that can help you. Okay, and the probability that you get help on the 8th try. So what does that mean? That the first 7 calls you make to people who can't help you. And then the 8th call is to one of the 2 who can. Okay, so how many ways can you make the first 7 calls to people who can't help you? There's 12 people who can't help you. The first call can be to any one of 12, second to any one of 11, and so on all the way till the 7th call. If you want, let's put in one more. Third to any one of 10. So you see you're subtracting 1 less, and the last call will be to any one of 6 people. And then the 8th call must be any one of 2. So that's a total number of ways you could call to finally get help on the 8th try. And out of all the possible ways is 14 times 13 times 12 times 8 times 7. Okay, or if you want, here we have 12p7 times 2 over 14p8. Okay, so that's the total number of ways, and I'll just write down the answer here because I don't have space. One, two, three, four, five, six, 7, and then you have that. So a bunch of this you can see easily cancels. All that will cancel with all that, and the answer you eventually have is one more little cancellation. 1 second. You have that goes over here 7 times. So the final answer is 6 over 91. Okay? That's the final answer. Okay, now the question next is, what if you have a total of n friends of which 2 can help? Then what's the probability you finally get help on the 8th try? Okay, it's the same kind of thing. Well, you have n minus 2 and you want to permute k minus 1. You want to pick k minus 1 from n minus 2 where order matters. And then the last could be any of 2 divided by npk. Okay, eventually what this will be, we can get hints from the previous one. We will have left over the 2. We will have left over k minus 2. not k, yeah, k minus 2. And in the denominator, we will have n, and we will have n minus 1, as you can see from that. Okay, so that's what you have. It'll be 2k minus 4 over n squared minus n, whichever way you want to write it, that's fine. Okay, now, question 2. It says, and of course we did use the assumption that we did not redial any friend in question 1. Okay, question 2. You have 4 distinct pairs of socks. How many different patterns can you make if you arrange them in a row? So you have 8 socks. Okay. And 2 are identical. Another 2 are identical. And another 2 are identical. And another 2 are identical. So the total number of arrangements would be 8 factorial divided out by the arrangements of each one of those pairs. And that's the answer. Okay, you can leave that like that. That's fine. I mean, of course, if you wanted, it would work out to be 7 factorial over 2. If you want, you could simplify it like that, because 2 times 2 times 2 is 8, so you could cancel with the 8 of the 8 factorial, be left with 7 factorial in the numerator, and 1 2 is left over in the denominator. Okay, now question 2 part B says, what is the probability that no sock is next to its partner? Well, this question is lot like example 5N from chapter 2 in section 2.5. If you look at section 2.5, 5N for November, it was, you have 10 married couples are seated at random at a round table, and no wife sits next to her husband. Over there you have a round table. Over here we're talking about a row, but the thought process is very similar. Okay, all right, so let's do that. Let's, in fact, we will do probability that at least one sock is next to its partner first. Okay, so first we will do C. We have to start labeling events. Let EI, okay, so first you can arrange the pairs by color or whatever you want, and call them pair 1, pair 2, pair 3, and pair 4. Okay, so once you have some labels on your pairs, then you can just mix them up. It doesn't matter. First, I just wanted to have, by any way you want to order them and give them names. Okay, my checkered one, my blue ones, or whatever you want. Just something is pair 1, something's pair 2, something's pair 3, and pair 4. Okay, and now we're going to have let EI be the event that pair I is together. Okay, and what do you want in part C? What is the probability that at least one sock is next to its partner? So you want at least one of the EIs to occur. That is exactly 1 to occur, or 2 to occur, 3 to occur, 4 to occur. It doesn't matter. You want some of this to occur. So that is exactly the union of EI, the probability of this union. Okay, now what does inclusion exclusion say? It says this will be the sum of the probabilities minus the pairwise intersections. You have to take EI intersect EJ and make all possible pairs. If you take E2 and E3, you do not then take E3 and E2, okay? And then you add the triples And then finally, there's only one quadruple intersection, so you subtract that. Okay, and now let's calculate these. What is the probability that the ith pair is together? Well, you have all these socks. Those are weird looking socks. 1, 2, 4, 3, and there we go. 4 pairs. You tie up one of them and make it like one unit. Fold it together. So you have now 7 units together. Okay, but of course, don't forget, you do have pairs still. Okay, so what is this probability? The total number of ways to arrange 7 items in a row is 7 factorial. But you have that these two are the same, these two are the same, these two are the same. So you're dividing it by 2 factorial, 2 factorial, 2 factorial. And you don't have to divide by 2 factorial for this one because it's already tied as one unit. You already thought of it as one unit. Total number of ways you could arrange it is 8 factorial over 2 factorial, 2 factorial, 2 factorial, 2 factorial. Okay, so that will be in the denominator, in fact, for all of them. All right, so that's EI. How many terms are there? There's 4 such terms. So if you want, you can simplify it now or later. We'll just leave it like this for now. There's 4 terms. So this is the first sum. Let's denote it in some way. Okay, so that's the first sum. Okay. And that's 4 terms in the first sum. And they're all equal to this value. Okay. Now let's look for PEI intersect EJ. What do you do now? Now instead of just having one pair tied up, now you're going to tie up 2 pairs. So how many units do you have? 1, 2, 3, 4, 5, 6. So that's 6 factorial. And then you divide out by the 2 factorial for the yellow and the orange pair, and divide it by the total 8 factorial over 2 factorial, 2 factorial, 2 factorial, 2 factorial. Okay, how many such terms EI, EJ are there? Well, what do you have? You just want to select 2 from 4. It'll just be 4, choose 2. You want to select 2 from 4, where order doesn't matter. So 4 times 3 over 2, and that is just 6. So there's 6 terms in double intersections. And they are all this quotient. Okay, now let's look at triples. Now what are you going to do? Go up and tie up yet a third pair as one unit. So now you have 1, 2, 3, 4, 5. So it's 5 factorial. And now only one is identical. So you have 2 factorial. Divide by the same thing. And how many such terms are there? There are 4, choose 3, or just 4, choose 3. That is 4 such triple intersection terms. Okay, and then what is the probability of E1, E2, E3, E4, the intersection of all of these? So that means now you've tied up all of them. Is just think of it as there's 4 distinct pairs that you're just going to arrange pair 1, pair 2, pair 3, pair 4 in any order. And the number of ways you could do that is 4 factorial. The total number of ways is, now you don't have to do any division or anything. 8 factorial, 2 factorial, 2 factorial, 2 factorial, 2 factorial. Then there's only one such term. Okay, so now let's put it all together up here. And what do we have? We will have all of it is over 1 over, I'll just write it as a common term outside, 1 over 8 factorial divided by 2 factorial raised to 4. Okay, and the first, there's 4 such terms, so 4 times 7 factorial over 2 factorial cubed, minus, then there's 6 such terms, 6 times 6 factorial over 2 factorial squared, plus, then there's 4 terms, which are 5 factorial over 2 factorial, right? And then lastly, there's 1 term of 4 factorial, okay? So this number over here is the probability that at least one pair is together. This we've used inclusion, exclusion, okay? And the answer to part B is 1 minus the answer to part A, to part C. Okay, the probability that no sock is next to its partner is 1 minus the probability that at least one of them is. Okay? All right, so I hope that made sense, and that takes care of the solutions to the quiz. Okay? Yes, of course, that looks a little bit massive. You could do some cancellation and simplify it, but my point over here was at least getting you to know how to do the problem. Okay? All right. So that's that. Now what I'm going to do is move on to the problems from the book that I was asked. Okay? So let's take a look at these, and the numbers I was asked are Chapter 3, 46, 63A, 74, 81B, and 93. Okay. All right. So let's do this. Okay. A lot of these problems you'll notice is they're about conditioning. And what you condition on is important. And sometimes what will happen is with these conditioning kind of problems is once you condition, you end up with the same probability that you were looking for, and then you have to do a little bit of algebra to solve it. And that technique you've seen in many different places. For example, in calculus, when you did the integral of e to the x cosine x or e to the x sine x, you did integration by parts twice, came up with the integral again, did a little algebra and solved for it. So over here, once again, you will have things like that, where you want to find a certain probability, you don't know it, but once you do some kind of conditioning, that probability appears again on the right-hand side amongst other stuff. Then you do some algebra and solve it. Okay? Anyway, so I will mention that more when we come to a problem like that. Okay, so for now, let's start with 3.46. What is that? That problem is says 3 prisoners are informed by their jailer that one of them has been chosen at random to be executed, and the other 2 are to be freed. Prisoner A asks the jailer to tell him privately which of his fellow prisoners will be set free, claiming that there would be no harm in divulging this information because he already knows that at least one of the 2 will go free. The jailer refuses to answer the question, pointing out that if A knew which of his fellow prisoners were to be set free, then his own probability of being executed would rise from 1/3 to 1/2 because he would now be one of the 2 prisoners that would be executed. What do you think of the jailer's reasoning? Okay, so this question is one where we will have to do some kind of smart conditioning. Okay, we can't just do some basic naive conditioning. We'll have to do very smart conditioning. Okay, so we have 3 prisoners, A, B, C. Okay, let's write them in lowercase letters, and G is the guard. Okay, A talked to G and was discussing, was trying to convince the guard to tell him which one of B or C would not be executed. Okay, now one's instinct might be to condition on events such as B is executed or C is executed, but we should not do that. What we should condition on is what the guard says. Not that the guard is lying, but the guard is purposely going to say something or not say something based on what the truth is. So, for example, the guard knows that C is going to be executed, then the guard will point to B. So there's some kind of decision making going on in the guard's mind. So here we go. Let me condition, and then you will see what I mean. Okay? So you really need to not just do this in a naive conditioning way. Okay? So let's create events just like we always have to. Let A be the event that prisoner A is I use a lowercase letter, not is executed or is chosen to be executed. Let B be the event that prisoner B is chosen to be executed, and C be the event that prisoner C is chosen to be executed. Okay, so that these events, they're so far obvious. And now G, that is the kind of thing that would come to you by doing conditioning examples. This is what we're going to condition on. Let G be the event that guard or jailer, it's a jailer, I should make him J, jailer says that B will not be executed. Okay, let me make this J. Okay, so let's also make this J. J is the event that jailer says B will not be executed. I'm not talking about whether or not B will be executed. This is the fact that jailer says B will not be executed. This is what jailer is willing to declare. We're not saying the jailer is going to lie, just like we'll see. Okay? It's important what the jailer says, because the jailer will tell you things with different likelihoods under different circumstances. So, for example, what is the probability that the jailer tells you that B will be executed, given that A is the one chosen to be executed? Okay, so what do you have? Here's A, and here's B and C. You know this guy has the big skull mark on him. He's the one who's going to be executed. And now the jailer, what's the probability that he'll say that B is not going to be executed? He could pick B or C. It doesn't matter. But both ways he wouldn't be lying. So the probability that he says B won't be executed in this case is 1/2. Okay? What's the probability? Jailer declares to you and says that B won't be executed given that B is the one who's chosen to be executed. Jailer is not going to lie to you. So jailer won't make this declarative statement to you. And in this case, it will be 0. What is the probability that jailer tells you that B is chosen not to be executed? B will not be executed given that prisoner C has been chosen to be executed. Now, what do you want? The jailer is over here. He's going to pick one of these two. Obviously, if this guy now has the skull over his head, what's the probability that jailer is going to pick B to say that he won't be executed? This will be 1, right? Okay, so this is what we're saying, it depends on the jailer's thinking, what he will speak, right? Okay, what is the question asking then? Does the probability change? Well, let's take a look. Okay, what is the probability of A? So let's write those down. What's the probability of A? We were told that randomly all 3 were chosen, and one of the 3 was chosen randomly. So each one of these is 1/3. Okay, now let's see. The jailer said, I'm not going to declare anything to you because if I say something to you, that will change your probability. Well, let's take a look. What is the probability that A was the one chosen to be executed, given that jailer made this declarative statement? Does it change? Does it become 1/2? Let's take a look. Well, what will this be? This will be P of A intersect J over P of J, and then just by conditioning, and then if you want, here's the step. Jailer will speak and you can take the whole sample space, divide it into 2. A is going to be executed, B is going to be executed, C is going to be executed, and do the intersections and conditioning. So you have A, P of A, this is just the Bayes theorem, P of J given B, P of B, plus P of J given C, P of C. Okay, now let's fill in these numbers. P of J given A, what's the probability that jailer will say B is going to be freed, given that A is the one who's picked? Well, jailer will pick A or B or C. This is just 1/2 like we discussed up here. Probability of A is 1/3. Okay, this is the same. You're always going to have one term which is exactly the same as the numerator when you use Bayes' theorem. What's the probability of jailer saying that B will be freed, given that B is the one who's chosen? That will be 0. And times 1/3, that doesn't matter, but still. What's the probability jailer is going to say B is the one chosen to be freed, when in fact he knows it is C? Well, that is 1 and times 1/3. Okay, so just work it out. If you want, cancel out the 1/3 and you're left with 1/2 over 3/2, and this in fact exactly is 1/3. So what do you see? The fact that jailer revealed some information to prisoner A didn't change his probability. It still stayed 1/3. It didn't matter that we picked that the jailer says B. If you could do the same with C, but you don't need to because it's a symmetric argument. What the jailer reveals to prisoner A about B not being executed, or maybe if he says about C not being executed, it doesn't change his probability. Okay, so that tells you that this equals, you should write this, since this equals P of A, jailer revealing this information to prisoner A didn't change anything. Okay, and similarly, if the jailer revealed that C will not be executed, you still have that in that situation, it's still 1/3. Okay. All right, so let's write that. Similarly, if jailer revealed that C won't be executed, the probabilities remain unchanged. Okay? All right, so that was 46, chapter 3, number 46. Okay? And now let's move on to the next problem, and that is 63A. Okay? Okay, what do we have over here? This says, in this question, you have a biased coin, and what you're trying to do is create a situation where you're using this coin where half of the time you say the result is heads and half of the time you say the result is tails. So you're using a biased coin to simulate a fair coin. Okay, so that's 63A. Okay, I will read it. Suppose that we want to generate the outcome of the flip of a fair coin, but that all we have at our disposal is a biased coin that lands on heads with some unknown probability P that need not be equal to a half. So the coin is biased. I mean, maybe we don't even know the probability, okay? And how do we use this? So what it says is, here's what you do. Consider the following procedure for accomplishing our task, and we want to show that this ends up, the result is equally likely to be either heads or tails, okay? What you do first is flip the coin, and then second, flip the coin again, okay? So you flip the coin twice. If they both match, then you restart the process and flip twice again. If they don't match, then the result of the last flip will be the result of the experiment. So for example, if you have tails, heads, then you say result of the coin flip is heads. If you have heads, tails, then you say the result is tails. If you have tails, tails, you start all over, and then the next two is tails, heads, then you say the result is heads. If it's tails, tails, heads, tails, you had started over here, then you say the result is tails. If you have heads, heads, tails, tails, heads, tails, then you say the result is tails, and so on. Okay? All right. Now, in this problem, what we need to do is, once again, we have to be smart about how we condition. And we need to do some conditioning. And what we need to do is, instead of conditioning on what happens in the tail end of the flips or the last few flips, what you should condition on is what happens in the beginning flips, and then you will see that the term we're looking for will repeat. All the coin flips are independent, thus you'll see that the term will repeat, okay? So here are the events that you will consider. All right, so let H be the event that the last flip in the procedure is heads. T is the event that the last flip in the procedure is tails. Okay? We only need to calculate one because the probability of the other will be 1 minus the probability of the first, because the procedure will either end in heads or tails, so they're complements. And so note that this is H complement. Okay, and now here are events that we're going to create to condition. Let F1 be the event that the first two flips match. Okay, let F2 be the event that the first two flips are HT. And let F3 be the event that they are TH. Okay, so we want to know what is the probability that we end our experiment, our sequence of flipping that we need to do with the heads. Well, what we will do is condition on F1, F2, and F3. You know it will end with heads in one of these three ways. Okay, so you have probability of heads is probability of heads intersect F1 plus probability of heads intersect F2, or if you want, here, let's write it first as okay, so that'll be the sum of the probabilities because they don't intersect. Right? There's no intersection. Either they're the same or the first two flips are TH or the first two flips are HT. Okay? And now condition. So this is what we're doing. We're conditioning wisely. Oops, sorry, that's a 1. Okay. All right. So I'm not going to start at the beginning. I'm going to start at the end. Okay. Let's start with this term right here. What's the probability that you end with heads given that the first two flips are TH? Well, this will just be 1, right? Because if the first two flips are TH, the two flips are different, and you end the experiment. All right. What is the probability of F3? What's the probability that first two flips are T and H? The probability of T is 1 minus P. The probability of H is P. So that is exactly 1 minus P times P. Okay? Make sense? All right, now let's move backwards and come here. What's the probability that you end with H if the first two flips are H and then T? Well, if it's H and then T, then you stop the experiment and declare the resultant flip to be tails. So in this case, that is just 0, right? This doesn't matter, but in any case, for the sake of completeness, this is P times 1 minus P, okay? All right, and now let's take a look at this. What is the probability of F1 that both flips match? So you want the probability that the first two are heads or the first two are tails? Well, the first two are heads with probability P times P. The first two are tails and they don't intersect with probability 1 minus P times 1 minus P. Okay? Okay, and then now let's take a look at this. What's the probability that you end with heads given that the first two flips were the same? In that case, what are you going to do? You're going to start the experiment again, right? It starts all over. It says go back to step 1. So this is in fact just P of H. Does this make sense? Because if you have TT, you stop and then start over. Or if you have HH, you stop, you start over, and then what happened, it doesn't matter. You would stop and start over, but that's embedded in there. So if the first two are the same, you stop and start over, and at that point, it's like you never flipped before, and the probability of ending in heads is exactly the same as what you originally started with. So that's what you have, and this is what I meant. You see the term you're looking for again on the right when you're solving it. Okay, so just do some little algebra, and you have P of H times 1 minus P squared minus 1 minus P squared equals 1 minus P times P. So P of H will be 1 minus P times P, over 1 minus p squared. Let's open this up. It'll be minus 1. Oh, here, let me not try and be a superhero. I won't skip steps. And you have this. Let's open it up. 1 minus p times p over 1 minus p squared minus 1 plus 2p minus p squared. And now let's cancel stuff. This cancels with this. And put the rest together. And what do you have? You'll have 1 minus p. 1 minus p times p over 2p minus p squared. Okay, so in the 2p minus p squared, minus 2p squared, sorry. Let's factor out 2p, and what are you left with? 1 minus p. Okay, beautiful. Now, once again, you can cancel. P cancels with p, and 1 minus p cancels with 1 minus p, and what are you left with is 1/2. So you have that the probability of heads is 1/2, and probability of heads complement, which is the probability of tails. H is the event that we ended with heads. It's not saying that one of the coin flips is heads. And this is T. Okay, if you want, you could put a H sub E for the event that it was ending with heads. Okay, so that's nice. So this way, with this unbiased coin, by flipping in this way and declaring the result to be the last flip of the first unmatched pair, you have that it's 1/2. You could have just as likely picked the first flip of the first unmatched pair. That would have given you the same result of 1/2. Okay.